Okay, we just learned that the electric potential is the potential energy divided by the charge. So therefore, the SI unit will be different from the unit of the potential energy. Okay, let's see. The SI unit of potential energy is, we call it 1 V, 1 volt, which is equal to 1 joule per coulomb. Why? The potential energy has the SI unit of 1 joule, and the electric charge has the unit of coulomb. Okay, so therefore, we divide 1 joule by coulomb and get the 1 volt. I think you are familiar with the word volt, because at home all of us are using the electricity of 220 volt, and then the finger-like batteries which you can buy from any market is typically 1.5 volt. And this name volt comes from the Italian physicist named Alessandro Volta, who discovered the voltaic pile, which is the first modern battery. Okay. And then let's reconsider the SI unit of electric field. Previously we learned that the SI unit of electric field was 1 Newton per coulomb, which was the SI unit of the coulomb force divided by the SI unit of charge, right? 1 Newton per coulomb. And then we just saw that 1 volt is equal to 1 joule divided by coulomb. So therefore, 1 joule must be equal to 1 volt multiplied by coulomb. And then from the mechanics in the spring semester, we also learned that 1 joule is in fact equal to 1 meter multiplied by Newton. Okay, 1 Newton multiplied by meter. Okay, and then now we see that here 1 joule and 1 joule here cancel out, and Newton also cancel out, and Coulomb cancel out, and what is remaining is just 1 volt per meter. Okay, so what does it mean? We previously learned that the SI unit of electric field must be 1 Newton per coulomb, but we can also use the same unit to be 1 volt per meter. So 1 Newton per coulomb is exactly equal to 1 volt per meter. And then what it also means is that if there is a 1 volt of electric potential difference across the distance of 1 meter, that is in fact equal to 1 Newton per coulomb. Okay. Okay, and then so far we have discussed only the SI units, but there is one unit which is not SI but very convenient, and it is called the electron volt. And then here again, please be careful not to be confused. The electron volt is not a unit of it's not a unit of electric potential, but in fact it is a unit of energy. Okay, a unit of energy. Okay, I am writing using my mouse, so it looks like a very bad handwriting, but please excuse me. And then for the electron volt, we write using small e and large v, which comes from electron volt, and then it is in fact equal to E, which is an elementary charge, multiplied by 1 volt. And then we already learned that 1 E is equal to 1.6 times 10 to the power of minus 19 coulomb, and 1 volt is equal to 1 joule per coulomb. So therefore this coulomb cancel out, and then what we get is 1.6 times 10 to the power of minus 19 joule. Okay, you see that? Now what we have is the dimension of energy. Okay, and then you see that in the spring semester we are familiar with having joule close to something about 1 joule or 10 joule, but here is 10 to the power of minus 19, so therefore it's a very small amount of energy. But then why do we use it? It is in fact if one elementary charge or one electron or proton experience the electric potential difference of 1 volt, then it will become 1 electron volt. So this is the potential energy of 1 electron when it fills the electric potential of 1 volt. Okay, so therefore the unit of electron, this unit is very useful for discussing atomic or subatomic particles like electrons or protons. Okay. Okay, then let's see how explicitly we can calculate the electric potential from the electric field. Let's first begin by considering how we calculated the Coulomb potential energy difference. And then it was equivalent to the negative integration of the Coulomb force along the path of motion, right? So we are now, in order to do the integration, let's first begin by writing it in a differential form. The small change in the potential energy was equal to the minus or negative of the small work done by the Coulomb force. And then how do we calculate the work done by the Coulomb force? Of course, it's the force dot product by the displacement. And then in this particular problem, the Coulomb force can be written as the test charge multiplied by the electric field, right? And then we integrate this equation from the initial position to the final position. So what we get is that the difference of electric potential energy, which is the difference between the initial position and the final position. So in this case, we are integrating the force along the path from the initial position to the final position. Remember, we still have minus sign here. And then finally replace the Coulomb force by the test charge multiplied by the electric field, right? And then eventually what we wanted was the potential difference, not the potential energy difference. And how do we get the potential difference from the potential energy difference? Simply divide it by the test charge, right? So we want to remove the test charge so that it becomes independent. So now finally, simply dividing the above equation by Q naught, we get the potential difference, which is the integration of the electric field along the path and from initial position to the final position. And then please remember we have a minus sign here, okay? And then this is actually called the line integral. And then probably you are familiar with integrating along x-axis or t-axis, which is straight, but sometimes it may not be straight. You can actually integrate along a curve. And okay, the example is shown here. Suppose you are doing, or suppose you want to calculate the potential difference between, say, this position and that position, and then sometimes this test charge may not be moving along a straight line, but it may be moving a very curved line like this. Then you have to do the integration following this curved line, always thinking about what is the relationship between this displacement vector and then the electric field vector at that position. Okay, so of course the angle information will go in, but this is the integration you have to do. And then of course we will not do very difficult problems. We will consider only simple problems, and most of the time we will move along straight lines. Okay, but remember this integral doesn't necessarily have to be along a straight line. Okay, and then remember that we take the initial position to be infinitely far away. Then there the electric potential could be set as 0. This is what we already did in the previous slide. And then we can now see what is the absolute value of electric potential at certain position, say here. So instead of difference, we can talk about the absolute value. How we do that? We are simply integrating starting from the infinite position. And then we can simply rewrite by changing the initial value and final value of the integration, and then minus will disappear, right? So therefore, if you remember at infinitely far away, electric potential will always become 0 because there is no Coulomb force. So therefore, following this logic, now electric potential, its absolute value, it can be written as the integration of the electric field along the path from the current position. In fact, final position is the current position up to the infinitely far away. Okay. Okay, then let's try one real example of calculating electric potential from known electric field. The case here is a positive point charge. Here we have plus Q, and then you see the electric field lines going out. And then if you take the definition of the potential from the previous slides, what we have to do is we are taking the positive test charge from infinitely far away down to the current position. Let's call this large R. And then this is the integration we have to do. And then what is electric field from positive point charge? It was KQ divided by R square. And then, in fact, the KQ are all constant. So if you, then we have to integrate only 1 over R square by dr. Then what do you get? Then using just something you already learned from high school mathematics, it becomes minus 1 over R. And then if you insert large R and infinity, this is what you get. And then you can see that the first term actually becomes 0, right? And then finally you can say that electric potential at the current position becomes KQ divided by large R. And then here we don't really need to use the large R's, but instead we will use small r, which is the most common symbol for the distance from the point charge. So finally the V, which is electric potential, becomes KQ divided by R. And then you can also use the graph to visualize it. So here in this graph, as a function of distance R, as the distance increases, the potential will decrease following the inverse relation. Okay, but then remember, actually we are in 3 dimensions, and this graph shows you only dependence only along one direction, but actually it doesn't matter. For any direction, the same dependence will occur. So we can also try to represent it using the 2-dimensional potential surface. So along x direction and y direction, you can see that same 1 over r dependence appears, and then also in between, same 1 over r dependence. So it just looks like a mountain. So imagine you have a ping pong ball over here, and then the ping pong ball will start to fall down, right? And this is exactly what the positive point charge may experience at this position. So it's, for the positive point charge, the positive test charge, the electric potential from the positive point charge will probably look like a mountain here. Okay, and then in fact, what will happen if you have a negative charge instead of the positive point charge? Then mathematically the equation looks exactly the same. The only one exception is that you will have a minus sign, additional minus sign, right? So then instead of the mountain-like shape, then you will have a dip. So now if you have a negative point charge, then positive point charge will be attracted, and then it will try to fall into the hole. Okay, this is how it will behave. And then what will happen if you have more than one charge and then or group of point charges? Then it's very simple. Remember, each point charge will contribute independently to the electric potential. So all you have to do is calculate the electric potential from each point charge, which is VI, and then make a summation. And in doing so, remember that electric potential are not vectors, but they are scalar. So you are actually doing the scalar summation. This is different from the case of the electric field, because when you are calculating electric field from a group of point charges, there you had to do the vector summation. But for the electric potential, you are doing a scalar summation.